Great. Thank you very much for the invitation. It's a great pleasure to have the opportunity to share with you some recent results. Sorry to not be here for real, but I'm here by the mind at least. So today I will give two talks. So the first one is about social cognition, which is like a big part of my interest over the last 10 years. And so first, I want to thank all the people that have the immense chance to work on those topics. Working on social cognition is also recognizing that science is a collective endeavor. And more recently, so I created the lab at the University of Montreal around three topics: computational psychiatry, so how to use mathematics for approaching mental health and neuropsychiatric disorders; precision medicine, how to tailor personalized therapeutics from data coming from smartphone to genomes; and social neuro-AI, which is how to reverse engineer the social brain and apply that to the design of new artificial agents. So regarding social physiology, which is like the main topic at the basic science level, my research is concentrated on what people have metaphorically called the dark matter of neuroscience, which is social interaction. Because more than 10 years ago, when we started these projects, the literature in neuroscience was pretty scarce regarding two individuals engaged in dynamical interaction, even less with more than two individuals. And paradoxically, social neuroscience was focusing on isolated individuals lying in a fMRI scanner and out of direct interaction. So we just saw how human-machine interaction can provide an entry point to study this dynamical aspect of social cognition, even in fMRI context. But in my case, what I developed is a technology called Hyperscanning-EEG, which is like the recording of multiple brains simultaneously during social interaction. And the road to artificial intelligence and social artificial intelligence was created by first trying to model mathematically how two brains interact in silico with computer simulation, and then trying to have those models interacting with a human in real time. So this is like the summary with emoji to simplify. So brain with brains, models with models, and brains with models. And now that I joined the Department of Psychiatry and Addictology at the University of Montreal, the idea is to combine this social neuroscience with systems biology and computational methods to achieve precision psychiatry and tailor those treatments using both our biological grounding and our social embedding. And for that, I follow more like a RDoC kind of approach, which is like a multi-scale and multidimensional perspective on mental health that try to rebuild up from the data and the phenomena our taxonomy of mental health, and trying to link those different dimensions together, and especially to add, because it's not part strictly on the RDoC paradigm framework, the social dimension with symptoms and social behavior. And so it's grounded initially on the study of synchronization within brain. I had the chance to do my PhD in the former lab of Francisco Varela, who was one of the pioneers about seeing the brain as a network and comparing to a peer-to-peer network at that time with the brain web. And here the idea is to move from synchronization within brain to synchronization between brain, and to approach neuroscience from a two-body perspective. So where you take the two brains in interaction as one system. And using these hyperscanning techniques, recording people doing spontaneous social interaction, in my case at the first, with nonverbal imitation of hand movements, like in this video. So this is the resting state, so they are not moving yet. Now they are starting to move their hands, but they don't see each other yet. So the two participants are in two separated rooms, seeing each other through a dual video system, while their brain are recorded simultaneously. And now they are seeing each other, and you will see that there is a turn taking. So like a spontaneous organization of the turn taking and the interaction between the two people. Even if it's nonverbal, it's like a dialogue with imitation. And so at first, what we show is that already, and we complement that with fMRI study with the team of Philippe Fossati at PT Salpêtrière. We show that social interaction is indeed different from a passive social perception, but it's only the tip of the iceberg, because depending on the role you are taking in the interaction and the context this interaction is unfolding. At that time, we were not in the pandemic, but clearly this is the kind of thing we are studying now. Depending if you're in a dialogue with spontaneous turn taking or more like a formal talk like this one, the brain reacts in a different way. And especially we demonstrated that in the case of the spontaneous interaction, reward system were involved. And so that has consequences, for instance, for education, where peer learning, for instance, seems to better work than just like traditional one-way teaching. And that could connect with my later talk about from machine learning to student learning. But what was more surprising is the discovery that indeed, in the same way that brain synchronization occur within brain for the integration of information during awareness, so that was the work of Francisco Varela, between brains, we can observe also those synchronization in different frequency band during social interaction. And we replicate this with from nonverbal to verbal communication. Then we expand to even arrhythmic interaction, such as affective touch, where we show that affective touch can not only diminish pain, so there is an analgesic effect of affective touch, but this analgesic effect is correlated to this coupling between brains and coupled with the correlated with the empathy of the two people. So those are consequences more like for the clinical alliance and care in general. And again, like in time of pandemics, touch has been like a sense that have been pretty deprived. And here we show that it has potential to have strong impact on phenomenology of pain, for instance. And more recently also, we show that attachment style and task that you are having socially with another person. So is it motor coordination or more like empathy giving and a dialogue with emotion? The relationship that you have with people, such as stranger, friends, or a romantic couple, will also have a strong impact on this coupling between brains. So now I will try to connect with the AI perspective and social neuro AI, which is the reverse engineering of human brains interaction to design social competent artificial intelligence. So when we discovered those interbrain synchronization, we had like more question and answer, and I had to work with not only other neuroscientists and mathematicians to try to model that, sorry, but also philosopher to try to disentangle the different factors at play in this phenomenon of interbrain synchronization. So we can measure indeed communication, so how reciprocal the interaction is, but also we are measuring, and it's a confounding factor, the similarity between the two brains. So because we are not just random number generators, intrinsically our brains look alike dynamically. And so even without communication, there is some spurious similarities, spurious synchrony between brains. And to account for the true interbrain synchronization associated with communication, we should correct for those bias and similarity factor, whether at neurobiological, behavioral, and cultural level. And so that's where the in silico social interaction start using MRI and DTI. I built up two virtual brain in silico and computed digital simulation of the spontaneous interaction between brains. So having like all the brain region connected with the anatomical fiber bundle extracted from DTI and recreating the perception action loop between motor cortex and motor behavior. So for instance, the hand movement that we saw in the earlier experiment, by coupling this motor cortex to the visual cortex of the other person and thus simulating the imitation of one brain by the other, and then closing the loop by doing the same way the other way around. And by doing so, we were able to show that those sensory motor loop between people actually account for part of the interbrain synchronization. And now, working with Jean-Pierre Changeux in Paris, we are trying to build a more multi-scale computational model integrating circuits and neural scales to be able to probe the impact of genetic mutations on those dynamics. And overall, even if it's not at the social level, here with other colleagues at the Mila, we are also developing those generative computational models to achieve multi-scale computational psychiatry and being able to probe how molecular modulation can impact behavior and ultimately social behavior. And so to finish, combining interbrain synchronization and social neuroscience in interactive context with those computational model of social interaction, I will present the intersection of those two realms. So a brain interacting with a robot. And so that's called the human dynamic clamp. It's a paradigm that we proposed with the team of Scott Kelso in Florida Atlantic University. The idea is to have the human coupled in real time through a computer with a model of a human. And what we are trying to do using this interactive paradigm is to extract functional information coupled with other data, such as like the genetics and clinical scores, to help in diagnostic, prognostic, and treatment choice. And more recently, moving to Montreal, which is one of the capital in the world for video games, we try now to adapt this paradigm that was more initially designed for lab experiment to more house context or clinical context in the hospital using computer video games or even holographic video games using mixed reality. So using the HoloLens helmets. And this in collaboration with a French company, Actimage, we designed the first prototype of this mixed reality video game where a clinician can on top see markers in real time while the participant is playing the video game. So here, for instance, the video game was called Pop Balloon because the children just had to pop balloons that appeared in the play area. And here we deep phenotyping, we are doing deep phenotyping. So we are collecting a lot of information. So here is a video showing this prototype. So you have a avatar showing tutorials and explaining how you should pop the balloon. You can see here the heartbeat is overlay on the participants. And we are storing in the profile of the participants their reaction time, their heartbeat, their trajectory in space, and using all those data and combining that with deep learning algorithms such as like autoencoder but we are also developing more advanced deep learning algorithm now with Mila. The idea is to create a latent space, better accounting for the behavior and the skills of the participants, to be able to have profiles and track the developmental trajectory of those profiles across participants and across patients. And ultimately, based on those profiles, the idea is to combine those profiles and go back to individual profile to find subgroups of participants. And as I was telling initially, to rebuild a taxonomy of subgrouping and a taxonomy of mental health disorder from the bottom up using data. So for now, we have mostly focused on the prototype with sensory motor skills, with popping balloons. But the idea is to go further and integrate socio-cognitive skills. But in that case, you need to integrate social interaction in the avatar. And so that's what we are starting now with a new program in collaboration with the video game industry in Montreal. So to combine dynamical systems with biologically inspired deep learning architecture to achieve a more social embodied agents. So moving from chatbots that are only disembodied textual interaction to 3D games, and even having mixed reality, extended reality avatar, and ultimately robots. So if you're interested, we recently submit a paper. It's available on arXiv, summarizing the roadmap for achieving social neuro AI. And with that, I thank you very much for your attention.